business optimization by using the example of a break-even analysis. Business optimization, also known as business analytics or business intelligence, typically has a strong motivation in the business side and in the quantitative analysis side of a business, with the goal to transform the business into better decision making and to create better insight in data, to improve the ability to make more forecasting and more predictability in terms of planning and risk awareness, and to yield better analysis or better results based on the underlying data that is received. Obviously, business analytics can only be conducted with examples that have data, and typically data that is numerical. So this is a specific field in terms of business or in business science that relies on data that is numerical or quantitative. These models then, or the data can then be used to create models. Models then represent some kind of real world environment or real world example. These data models can then be used to create simulations, which obviously are cheaper than simulating or doing the same thing with a real environment, where there could be a waste of materials, where there could be a waste of costs and resources. Therefore, data-based modeling creates a optimization on the cost side, but it can also create an optimization on the decision side in helping decision makers in a business to create an outcome or to simulate an outcome or to look at potential outcomes based on the data, on the historical data of the past. One typical example that is used a lot, and it's a very basic example for business optimization, is the so-called break-even analysis. The break-even analysis relies on a specific point that we call the break-even point, which you can see in the arrow in the middle. This break-even point is to be established by understanding all the costs and by understanding the revenue of a product. The break-even point, typically in a break-even analysis, is the point in which all costs are covered, so that if a product is sold above this break-even point, the company can make a profit, or if a product is sold below the break-even point, the company might make a loss. And you might think this is an easy thing to think about. This is something that might not need business optimization. However, it is often difficult for a company to completely consider all the different types of costs. So what you see on the left-hand side, which is indicated in red, is typically the so-called loss zone. And the loss is a product often based on not knowing all the costs that are going into a product. These costs can sometimes be more than that meets the eye or that is obvious. Therefore, break-even analysis allows a company to clearly, or a decision maker to clearly analyze at what point, considering all costs, is the company going to make profits, and what point then is how many units need to be sold to cover all the costs. So this is not so much an analysis to decide on, okay, one product has a certain amount of cost and then a certain amount of sales price, or a certain amount of a certain amount of revenue dictated by the sales price. No, this is more an analysis that is based on how many units does a company have to sell so that all the costs that have been taken into account are covered. And you can see the costs on the right-hand side. Typically, these costs are variable costs and fixed costs. Therefore, this analysis gets a little bit more difficult, because the variable costs are the costs that can be accounted to the unit, such as to produce the unit, such as if you take a car as an example, the materials that go into a car, those are variable costs. Those are costs that can be directly accounted to the unit that has been produced. And the fixed costs, a little bit more complicated. The fixed costs are costs that always are to be paid. Fixed costs are typically rent, typically electricity of a product facility, typically salaries for the marketing department, for the CEO, for the leadership, and so forth. These costs are fixed. They always have to be covered, no matter if a single unit of this product is sold or hundred thousands of these units are sold. Therefore, we're looking for a point in the break-even analysis where all of these costs are covered, and how many units do we have to sell so that all of these costs are covered, and we can start thinking about a profit. Another typical optimization model, which we won't talk about in this presentation, is overbooking an airline, which again needs to be considered with these models and understanding. And the third one, which is very interesting, is the question of how a product should move through a production line, or maybe how a UPS van or some kind of transport van, the postman, should move through a grid on the map so that the path is the least cost, or the path has the least cost associated by saving distance and saving time, such as that the product, such as that the petrol costs so low, which is also known as the traveling salesman problem. So those are three typical problems: the break-even analysis, the overbooking of an airline, and the traveling salesman, where we're trying to move products through a graph-like structure in the most optimal way. So what we typically want to do is we want to increase revenue, decrease costs. We want to optimize something in terms of making it more time efficient, making it more resource efficient, such as maybe even in a supermarket, a queue, like at a Starbucks coffee. And there we would like to know, okay, do we need to open a second till, or is it enough to have one till because it might just be peak hours or it might just be random? So let's have a look at the break-even analysis just as one simple example. The break-even analysis does try to create a equilibrium, so to say, between revenue and costs. So we're looking at a point, we're looking at a specific break-even point in which all costs are covered. How many units do I have to produce or sell in this case, so that all costs are covered, and therefore any additional unit I will sell will create profit for the company. The different costs we have to think about. I mentioned fixed costs and variable costs. I will also mention mixed and semi-variable costs. The fixed costs are pretty straightforward. Fixed costs are fixed costs are always fixed. So a company has to pay these no matter how many produced units are sold or not sold. These fixed costs are typically salaries, such as for a marketing department, such as for the sales department. These fixed costs are typically rent. These fixed costs can be, sometimes their mixed costs can be, such as electricity or water for the production plant. Variable costs are directly associated with the unit that is produced, such as, again, our car example. The metal that goes into the car can be weighed. The metal that goes into the car can be specifically attributed, and in a more controlling terminology, it's a direct cost to the cost unit or to the produced unit. Mixed costs are usually combinations of both, so that could be something like electricity or water. Things get very complicated in a big production plant in terms of controlling, in terms of cost distribution. If we're producing 50 different models of cars in the same big production plant, then often these shared costs have to be associated to the different models that are car models that are produced in the plant, which could be maybe trucks even, or smaller cars, could be even lawnmowers. So smaller units obviously will require less electricity, but it's often not that easy to attribute this, because maybe the electricity also is the lighting of the entire building, and light obviously is then used by all the different production lines in the same way. And that might need some kind of spatial distribution and so forth. So those more detailed cost analysis in a company are typically called controlling, and a controlling function has to understand exactly how much the end unit that has been produced costs the company, with all the costs factored in. But in this simplified model, we're just looking at fixed costs and variable costs, not so much at the mixed costs and the semi-variable costs. Those are costs that typically, I just want to mention them here, but those are costs that typically go into a more complicated calculation, which we know as being controlling, or being something that the chief financial officer of a company really has to deal with. So typically what cost remains if the same, so just these are simple checks that you can ask yourself to see if you've understood everything so far. Which type of costs remain the same in total when units produced or sold increases? Obviously those are the fixed costs. Which type of costs remain the same per unit when units produced or sold per unit? when units produced or sold or increased, those are typical the variable costs. So if it's per unit or in total, those are things you have to think about. Assumptions for the model. Following assumptions we have to apply. Models always apply assumptions, which means they reduce reality. So we reduce reality to a simple model by taking a lot of different variables that would be into reality out of the picture and only focusing on very few variables. So here we're looking at one product or service, not at multiple ones at the same time. We're looking at fixed costs and variable costs that can be clearly separated. Again, as mentioned in the slide before, that's sometimes not that easy. And variable costs are linear in this case, which means the more I produce, the more exactly in proportion my variable costs go upward. That's not always the case with all products. Sometimes if you produce more products, you get economy of scale. You can get that in an exponential way. You can have the costs sink very quickly by producing very large numbers. We're looking at $1 of revenue per unit, so a very kind of simple way of looking at the chart. So why do we need assumptions? Obviously, we need assumptions to reduce reality, to make our model fit for calculation. If we have variables, and we won't need this in this analysis, but if we have variables that are more random, then we have to introduce random numbers into our model, which is typically used in simulations where random numbers are introduced, which create a randomness in our model and ensure that the model is closer to reality. The break-even equation is very simple. You take your revenue, which is the price tag of the product when it is sold, and you minus the costs, all the costs, fixed costs and variable costs in our example. We're not looking at all the pre-sales costs. We're not looking at all the costs to get into distribution, to equate to marketing campaigns and so forth. Obviously, in controlling the costs can be a lot more complicated. But here we just look at revenue minus costs. And that is what we call profit. That is what the company can take to reinvest. That is what the company can take to pay their shareholders dividend. That is what the company can do to exist, basically, and to survive. So profit always has to exist. Otherwise, a company will sooner or later fall out of business. But obviously, this equation is really important because you can now already see that if the costs are bigger than the revenue, then the profit will be negative, which means a negative profit will also destroy a company very quickly. We've replaced revenue, we replaced cost with variable cost and fixed costs, so that's pretty easy to take apart. And we know that the break-even point we're looking for is where profit is zero. So we're at that point where all our revenue covers all our costs, and that means we set profit to zero, and then we get an equation that we can resolve into whatever variable we need. In this case, we take revenue equals all variable costs plus all fixed costs. We can then go a little bit more into detail. We can say, okay, revenue also equates to all variable costs, means all units sold multiplied by selling price per unit. So we know that that's the equation for revenue, and then we can put this into our equation and we can say, okay, variable costs equals all units sold multiplied by variable costs per unit. So things can be resolved a little bit more complicated or detailed, whatever is needed. So if we look at this in a graphical way, very straightforward, again, based on our model assumptions, our revenue line here is a yellow line. So the more units we sell, the more revenue we get. A very kind of simple, a very, very, very simple equation. And we can go to the 100. And if we go to the 100, we can see that 100 units will be sold. If I sell 100 units, then I will make a revenue of 3,000. So if I take 2 zeros out of this, so I know that each product in this case is sold for $30. So this will be little model cars in my car example, obviously very small cars, $30 per unit. Now we're adding the costs. So the variable costs, pretty straightforward. If I produce no units, if I sell no units, then my variable costs are zero. But the more I produce, the more these costs increase. So if I take my 100 again, at the point of 100, I have $1,000 variable costs. So my material cost to produce 100 units is $1,000, and I'm selling for 3,000. So you can already see that I have $2,000 left to cover the rest of my costs, which are the fixed costs. So this gap between revenue and variable costs here now, this gap is what I have to cover my fixed costs that occur every year. So my fixed costs in this model presented, these are just modeled numbers, is 2,000. So therefore, I know that, okay, if I have 2,000 left to cover my fixed costs, then it actually hits that straight out. So my guess at 100 was correct. I've kind of seen that already a little bit in the model. I can go to 100 and I can say, okay, if I now take this difference here, mathematically the difference between the brown line and the blue line at 100, and if I look at that difference above the blue line, then mathematically that would be the same. It would be most likely that 1,000 units that I can cover with it. So if I take this now as a total cost, like I said, if I mirror this and I take the fixed cost, so I start at 2,000 and I take the same slope that the brown line has, which is the variable cost, and I shoot that up. I just start at 2,000 where the fixed costs are. So if I'm selling 0 units, I still have to pay 2,000. So I'm basically shifting the y-axis in this case, and then I'm going to hit my revenue curve at around 100, and that is my break-even point. So I can already see that 100 is my break-even point. So I need to sell at least 100 units so that I can break even. So in terms of business optimization, I need to know this before I start producing, because otherwise I won't be able to cover my fixed costs. There are different models out there, different thought systems out there that say, okay, if we have a new product and we're promoting a new product, then we can sell under the break-even point, but we should never sell under fixed. So we can sell under break-even point. We can reduce our revenue to the point that is related to the fixed costs. So because we have to pay the fixed costs anyway, so short term we can run underneath, but we should never ever sell products below the variable costs. So if we take this variable cost per 100 units, so I now know that the variable cost is $10 per unit. So I can take my $30 revenue, I can drop that to $20 if I want. Which means I am going to make a $10 deficit, but this $10 deficit is still not going under $10, and therefore I can still survive short term because I have to pay fixed costs anyway. So these are just thought systems in terms of new products that are launched. You can drop below the break-even point, but you should never in this case drop below $10 in terms of revenue, because then every time you sell a product you're going to pay on top, because you actually have to always pay the variable costs, which are the materials. So you will very quickly kill a company if you go below variable costs, but you can for a very short time go below the revenue point above variable costs. And that is our break-even point, and this is the point in which we can optimize. So we can move our units back and forth. So now, because we have the mathematical model, we can clearly find out, okay, if we sell 125 products, how much profit will we make? If we sell 150 products, how much profits will we make? And we know that if we sell more than 100 products, we will make profit with each one we sell, and we know that we will lose money, we will make a deficit with anything that is below 100 units. So our break-even point is 100 units. And that is our profit zone, and this is our deficit zone. So if we look at another example, if we look at a dinner show in a theater, a very simple dinner show in a theater, our facility costs are 500, our staff is 1,000, kitchen staff is 200, storage crew is 300, and food costs per ticket are 10. Ticket price is 30. Calculate the break-even point by the numbers. So I'm going to run this briefly just to show you the example. It's pretty easy now to see what you have to do. You basically first have to look for the fixed costs, and then you look for the variable costs. The fixed costs are costs you have to pay anyway, no matter how many tickets you sell. So you will have to pay the facility, you will have to pay staff, you will have to pay the kitchen, you will have to pay storage, and you will not it's basically that's your fixed cost. In terms of variable costs, you will have to pay food per ticket. So the more people buy tickets, the more food you have to buy. So $10, 10 units, basically, or the per unit buy per ticket, you will have to buy $10 of food, or you will have food costs of $10, which means if you look at the ticket price, you can immediately see there's $20 left to cover the fixed costs. So you could do a very simple example. You could just add up the fixed costs and divide it, and try to find it that way. But with the break-even analysis, it's a bit more programmatic. So we now have our fixed cost of 2,000 total. We have our variable costs of 10 per ticket, and the question obviously and then we have the revenue of 30 per ticket. And now the question is, how many do we have to sell? So we plug that into our equation. So our equation, we know revenue minus cost is 0. So where profit is 0 is our break-even point. So we know revenue is 30 per ticket. We know our variable cost is 10 per ticket, and we know our fixed cost is 2,000. We plug that into our equation. We now resolve the equation by pulling the similar values into 1. So we now know that we have $20 per ticket left after paying our variable costs, and we have 2,000 fixed costs. So how do we work with that? Basically is we take our 20 and obviously divide it by the 2,000. We divide 2,000 by 20, and we get again 100 tickets. So we need to sell at least 100 tickets to cover our fixed costs. So pretty straightforward, because we know our fixed cost is 20 left revenue from the ticket to cover the 2,000 fixed costs. So if we look at this again in the break-even analysis, it's kind of the same, very much the same example.